Welcome back, everyone. In this lecture, we are going to learn how to use two-dimensional geostatistics to interpolate layer elevations to your MODFLOW grid. Specifically, in a MODFLOW grid, each cell in the grid has both a top and a bottom elevation. And these are used as part of the discretization file. And they're edited in the Global Basic Package Dialog in GMS. We've built a few models by now, and we've seen those. It's a set of arrays. And so suppose you had a grid and then you had, for example, some borehole data. You could then use the geostatistics and interpolation tools to interpolate the points off of the boreholes to define the layering in your MODFLOW grid. And this is done using something called 2D geostatistics interpolation tools that are part of the 2D scatter point module in GMS. More specifically, for a multi-layer MODFLOW grid, every cell or every layer has an array of top elevations and bottom elevations. And theoretically, it's possible for the bottom elevation in one layer to not match the top elevation in the layer below. There's a way to do implicitly defined confining units, but in GMS, the assumption is made that for example, the top elevation of layer 2 is equal to the bottom elevation of layer 1, and so forth. So therefore, if you have, in this case, a 4-layer model, it's shown as a 3-layer on the left, but the diagram on the right is actually a 4-layer model. You would end up with 5 arrays, top 1, top 2, top 3, top 4, and bottom 4. And so we have to do something to create those arrays. A lot of the models we've been creating thus far in class, we've just used a constant top and bottom layer elevation. But in reality, you want to more accurately represent the geometry of that layering. And so today we're going to talk about some tools for doing that. And as we do that, typically we do the top elevation of layer 1 a little bit differently than we do all of the bottom elevations for a multi-layer model. And the reason being is your top elevation of layer 1 typically corresponds to the ground surface. And we often have very detailed ground surface elevation defined as part of a digital elevation model. Furthermore, there's a way in GMS to very easily get DEM data, ground surface data, for basically anywhere in the world. The steps are, you go to the File menu, select the Import from Web command, locate your region, select World Elevation Data, and then interpolate from the resulting DEM to your MODFLOW layer array. So when you select the file import from web command, this map locator comes up. When you first bring it up, it will show a map of the entire world. And then you can either just zoom in to a particular location, or you can type in the name of your location in this search bar right here. So for example, Brigham Young University is located in Provo, Utah, so I typed Provo, Utah and clicked jump to search location, and it automatically zoomed in on this location. Once you do that, you click OK, and then it brings up the data service options. You can actually import lots of different kinds of data using this. Some of that comes in as polygons to the map module. Some of it comes in as a base map. But if you scroll over and pick this World Elevation Data option, and then click OK, it will then download a DEM in the form of a TIFF file. And once you have that in memory, it shows up on the Project Explorer window on the left. If you right click on that, by the way, when you click OK, it actually downloads it to a local file parallel to your GMS project, and then it lists it in the Project Explorer window. If you right click on it and then select Interpolate to, and then interpolate to your MODFLOW layers, that will then, you can use that to generate your ground surface elevations. And this interpolate to MODFLOW layers, I'm going to show you some more details on that below, but this is the basic step involved. So in summary, you can use a web service to zoom in on just about any location in the world, and then download, relatively dense DEM data, certainly sufficient for most groundwater models, that will provide your ground surface elevation, which is typically the top elevation of layer 1. So what about the other layers, your subsurface layers? Well, in this case, the first thing we typically do is we either import or create scatter point sets using data from boreholes or cross sections or whatever source you have for a set of points defining the elevations of each of the subsurface layers that you're trying to create. And then we interpolate those to the MODFLOW layer array. This is a cross section through a grid. And in some cases, such as the two cases shown here that are actually featured in one of the tutorials we're going to do in class, if you end up with, after the interpolation, with some layers that overlap one another, there's some utilities built into GMS that allow you to fix those, so you can end up with properly defined MODFLOW layer arrays as shown on the right. So now we're going to drill down to this process in more detail. And so the first step is to create what are called scatter point sets. This is one of the fundamental object types in GMS. If you are familiar with ArcGIS, this would be equivalent to a point feature class, where a scatter point set contains a set of points, each of which has an XY location. And then we can have what in GMS we refer to as data sets. So that would be like an array of values, one per point. So this would be similar to attributes in a feature class in ArcGIS. And so what's shown here is in the Project Explorer window, there are two different scatter point sets. One called ELEVs, and it has two data sets associated with it, bottom 1 and bottom 2. And then there's another scatter point set called terrain that presumably is used to represent the ground surface, and it has a data set called elevation. And you'll notice in this case the ELEVs scatter point set and the bottom 1 data set are highlighted. That means they are active. There's one active scatter point set and one active data set at all times, and that is kind of the default set from which you can interpolate. Okay. Okay, next, how do we get these scatter point sets into GMS? Well, the first thing you do is you prepare a tabular scatter point data file. This is just a flat file, we call it. I'm going to show you an example in the next screen, but basically it's each row has the XY location and then whatever data set values you want. And once you've done that, and you can do this in Excel or Google Sheets or just a text file, and then if you prepare them in a text file or a CVS file, you can then import that to GMS using the file open command and just select the file. Or you can select your table in Excel and then copy it to the clipboard using Control-C, and then you go over to GMS and select Control-V. And in either case, whether you've imported a text file or whether you've pasted from the clipboard, GMS will then launch the text import wizard, which I'll show you how that works in one of our subsequent slides. So this is what a sample scatter point data file looks like. This particular one is loaded into Excel. You'll notice in this case we have a header row that has the titles for each of the columns. That's fairly typical. And then, so the first column would be an ID, and then we have the X and Y coordinates. You can do this as lat long as well. And then, depending on your projection you're using. And then you have one or more data sets, and each of which has a name. So in this case, top of layer 1, bottom of layer 1, bottom of layer 2, bottom of layer 3. And then, whether you save and open this file or whether you copy and paste it from the clipboard, it launches the text import wizard. And the first thing you do is, this is similar to if you've ever imported a text file into Excel. This looks very similar. Up at the top, you tell it what your column delimiters are, space, tab, comma, whatever. And then down below, it will show you with these vertical lines how it's interpreting the columns from your data. And then if you have a heading row, you want to toggle this on. Make sure you do that. And that basically tells it to skip row 1. And then you select the next button and it takes you to step 2. In step 2, it's very important. Oh, this is in the wrong order. The first thing you do up above is you select your data type. And you want to select 2D scatter points. It turns out there are several text formats that can be imported very easily into GMS, and this is just one of them. So you have to tell GMS what it is you're importing. And then for each of the, so what it does in the bottom of the import wizard, it shows you a preview of your data. And then for each of the columns, it has a little selector that allows you to indicate what is represented in each column. So if the column header says X or Y, it'll automatically match that up. Or if it has some other name, you need to tell it, well, this is X and this is Y. And so the first one, this is an ID, so you would need to use the little pull-down menu here, selector, to tell it that it's the name or label or ID of the data set, which hasn't been done yet. And then if you have a data set, you just need to mark it as a data set column. And then it will, by default, use whatever is in the header as the name of that, or you can type in here and give it a new name. Once you do that, you click Finish, and then that will successfully import your scatter points, and you will see the scatter points appear in the window. Now, once your scatter points have appeared, they will show up in the Project Explorer window under the 2D scatter point data folder, and then you can right-click on those and select Interpolate to, and then you can interpolate to any one of these objects. The 10, a 2D mesh, or 2D grid, 3D grid. But typically, in the context of what we're talking about, you typically want to select Interpolate to MODFLOW layers. There's also a way to get at this through an Interpolate menu in the 2D scatter point module. You can do it that way as well. And then once you interpolate, in general, it creates a new data set on the target object. unless you're going directly to the MODFLOW layers, in which case it populates the MODFLOW layer arrays. So once you select that interpolate command, it brings up the interpolation options. And up here at the top, you can, in general, you would tell it what you're interpolating from and what you're interpolating to. This one is hardwired because this is part of the Interpolate to MODFLOW layers. And then, there's some options on log interpolation and anisotropy that are a little bit more advanced. I'm not going to talk about those today. We'll talk about those when we go through the examples in class. But what I want to focus on here is there are 5 different interpolation methods or algorithms supported in GMS. And for most of these, once you click on it, there's an options button that comes up that brings up options specific to the method in question. Except for linear. Linear interpolation doesn't have any options. It just happens. But for each of these other 4, there are some options that you can select. Except Kluft-Toscher might not have any options either. But I know IDW, Natural Neighbor, and Kriging, you can select some options from that. Especially Kriging. Kriging has a large number of options. Actually, no, I take that back. So the option button is parallel to the method. So these are the options for inverse distance weighted. If you selected Natural Neighbor, then this options button would be undimmed. If you selected Kriging, then this option button would become undimmed. All right, now for the next few slides, I want to talk about each of these options, and we're just going to do a very cursory, high-level review of what these mean. If you go to the GMS documentation, you can find a complete set of equations and a pretty thorough discussion on how these work. The one that really is the most complicated is Kriging in terms of what you have to do to set it up, but it's also the most accurate of the 5. The default option is inverse distance weighted. It gives you pretty good results, and it's mostly black box. Usually you can just go with the default options. But let's look at how each of these works. And so to just give us a basis of comparison to compare these schemes, I'd like to use this example. I just made this one day in Excel. I basically coded up the formula for an elliptical function that looks like this. So if you're looking down in plan view, you can see those blue contours, and kind of in an oblique view, you can see it on the right. It's just a smooth dome that has an elliptical shape. And then I randomly created a bunch of points shown by the red dots, and for each of those points I evaluated that elliptical function based on its location, and then sampled the function value. And so we have, for example, right here, it would have some value from up near the peak of this function. And over here it would be something down near the edge, and everything out here has a 0 value. So this one's a little tricky. It has a distinct continuity or discontinuity right here, and most of our elevation data doesn't look like this. So this is kind of a challenging problem, but it helps us kind of get a feel for how these work, because we know intuitively when we look at a result how well it reproduced this. So let's go ahead and look at some of these. So this is when you run the linear interpolation. And again, now we're just going off these sampled values at the red triangles, and then from that using the interpolation to kind of reproduce. So what this thing on the right should look like is this shape right here. So if you use linear interpolation, what it does basically is it connects each of these points with a set of, or it basically triangulates these points. So you can kind of see that if you look at these contours on the left side and on the right, if you look at the shape, you can see those triangle shapes. So it creates a set of triangles, then it linearly interpolates the surface using the formula for each of those triangles, and you end up with this shape on the right, which is linear. It has these, they look like little tiles or flat surfaces that are pieced together. And so it's not great, but it's not bad. If you have really dense data, like a DEM that you've downloaded from the web that we talked about, the linear method works great because it's super fast and it's very simple and predictable. If you have sparse data like this, it's probably not that great, but it works. So that is example number 1. And so this is example number 2. This is inverse distance weighted interpolation. And there are different flavors of inverse distance weighted, one of which is to use what we call constant nodal functions. It's the simplest and most common form of IDW interpolation. So if you look on the left, I mean, that is kind of representative of what we have. So if you look back here, it's supposed to be this shape. And it captures a lot of the characteristics of that, but you can see it's got a lot of bumps and hills and pits. But it's not bad. Now another method is called inverse distance weighted with gradient planes. Now in this case, instead of just interpolating the value at each point, it actually fits a planar surface at each point and then kind of blends them together, so you end up with kind of a smoother shape. So if you look in the interior here, now the contours right around where that dome appears are fairly accurately represented over here. So we have the dome shape in the middle. The only thing that's a little odd here is it goes down below that flat surface. Now again, that trying to reproduce that flat surface, it's not the kind of thing you normally do when you're interpolating layer elevations, so it's quite challenging. And it ends up shooting past those, as you can see. However, there is an option back in the interpolation options here to truncate values, truncate to a specified range. So what you can do is you can say, well, if you have any value below 0, just truncate it to 0. So you can kind of give it a max and a min. And if you do that with this gradient plane option, if you turn on that truncation option now, whereas before we had these parts that were dipping below 0, you can make them flatten out, and now we're looking pretty good. So this is this looks very similar to our quadratic control function. So it's not a bad method. So then, excuse me, elliptical control function. So this is the gradient planes, and this is quadratic. So I've actually done, I skipped something here. So this is using the gradient plane function, and we could have truncated this and got similar results, but we skipped right ahead. There's another version of IDW that uses what are called quadratic nodal functions, and they're just a little bit smoother, but it's very similar to the gradient plane option. And you can see in the middle the contours are pretty much the same. And so that's not bad. And then another one we have is natural neighbor interpolation. That one works pretty well. And again, this is truncated, so we get a pretty good shape in here. This one is a pretty popular interpolation method. And then finally, we have what is called kriging. To use this one, we have to set up what's called a variogram. And there's a process involved in doing that, which I'm not going to go into. You can read about it in the documentation. We'll go through an example a little bit in class. It's not terribly difficult, but you do have to set that up each time. But what I want you to notice here in the middle, if you look at the shape of these contours, these most closely resemble our elliptical control function. So again, if you look over here on the right, that is almost identical here in the middle. We do get a little bit of oscillation over here on the edge. Again, I wouldn't worry about that too much. It's a kind of an extreme example, but in general, kriging, when you're working with sparse data, kriging typically gives you the the greatest accuracy. So I made this little table that helps you kind of look at some of the features of each of these techniques. I didn't include a graphic of the Kloff-Toscher results. That they look kind of similar to linear. It uses the same triangulation method, but instead of doing a linear interpolation, it uses a little bit of blending. So those two are fairly similar. Something I haven't talked about in these examples is some of these will extrapolate and some will not. So linear, it will only interpolate inside the kind of what we call the convex hull of the data points. Once you go outside of that, it won't do it. So it just assigns some kind of default value. That's okay if the thing you're interpolating to is entirely contained within the scope of the points. But if you want to interpolate to something that's just outside the points, these first two methods won't work. IDW and kriging work really well on that. Natural neighbor, there's kind of a way to do it, but it's not great. And speed, I mean, they're all very fast for most things you're looking at. Honestly, with today's computational power that's available and the kind of data sets you're working with, I wouldn't let speed be a determining factor. They're all pretty fast. Ease of use, linear and Kloff-Toscher do not require any setup. IDW, I would say natural neighbor, that should probably have a green dot as well. There's nothing to set up there. I don't know why I put it this way. And then kriging, it has a lot of setup. It's not black box. You have to do some manual setup every time. And then both IDW and kriging will extrapolate. And then in terms of accuracy, IDW natural neighbor somewhere in the middle. The other two probably less accurate, and kriging would be the most accurate of those. All right, so let's suppose you have everything set up and you select the Interpolate to MODFLOW layers command. Basically what that does, normally when you interpolate from scatter points, you're interpolating to something like a two-dimensional grid or a 10, and it creates a single result. With this particular option, you can actually interpolate multiple data sets at once. So, for example, if you have a scatter point set and it has multiple data sets associated with it, representing, for example, different picks along a borehole for different layers, you can interpolate those all at once. So what this dialog allows you to do is associate each of your data sets with a target MODFLOW elevation array. And so in this particular case, so what you do is you select something, you select two pairs at the top and select map, and it creates a linkage which is then shown at the bottom. And so this means interpolate the top one data set to the top elevations of layer 1, interpolate the bot 1 data set to bottom elevations layer 1, and so forth. So again, this dialog is simply used to create targets for each of your data set in the MODFLOW layer array. And you can also click on the Interpolation Options button, and it will go back to the Interpolations Options dialog that we saw before. And anyway, you click OK, and then it interpolates all of those elevations at once. Works great. Once you do that, in some cases, the interpolation process can create some errors. For example, if you look at the layers shown here, the top elevation of layer 3 is above the bottom elevation of layer 1, so that middle layer becomes inverted. And if you run the model checker, it will look for these errors in your layer arrays. So for each cell, it checks to see if is the top elevation above the bottom elevation, for example. And if it finds an error, it will report that. It'll tell you in the model checker that you have errors, and then you click on a button called Fix Layer Errors, and it will show you on the right, in this particular example, and it's not associated with this graphic, by the way. It says Layer 1 has 582 errors, so there would be 582 locations where there were elevation errors found. And then it has a set of, it says correction methods. These are just different algorithms it uses to fix those. And basically it's going to, so preserve top would be that if you have an overlap, it just keeps the top one where it is and clips the bottom one so where it's just below it. Preserve bottom says, well, keep the bottom one intact, but clip the top one, as shown here. And then there's another one we call truncate to bedrock that does another kind of clipping to the bottom array. And the best way to learn how these work is to go through some examples, which we will do in the tutorial we'll go through in class. Once you do that, you can actually use it to model some fairly interesting things. The one on the left we refer to as bedrock truncation. So this would be kind of a case where you had some alluvial fill, some relatively horizontal layering inside a kind of a channel-shaped bedrock or a valley. And that can be set up using the bedrock truncation tool. And in other cases, maybe you have a lower layer that outcrops at the top, so the fixed layer error thing can generate data sets or results that look like this as well. So again, there are ways to fix those errors. There are some tools involved to help you do that, and the best way to learn about that is to go through them. So that completes our introduction to layer interpolation and 2D scatter point sets, and certainly encourage you to learn more about that by doing. It's actually a relatively intuitive and fairly easy thing to do, and it's kind of fun to generate these more realistic 3D stratigraphy models. Thank you.